Good morning. Today I will do some more problems on reflexivity, symmetricity, and transitivity. Group, let me make one thing very clear that in the topic of relations and functions, you have to do three topics: types of relations, one-on-two functions, composite and invertible functions. You don't have to do binary operation. I make it again very clear, you don't have to do binary operation. It's cancelled now. Fine. Now, my first problem to you is define a relation R on set of reals is A, comma B such that A is less than or equals to B square. Is R reflexive, symmetric, transitive? See, whenever the relation is reflexive, you have to prove it. If it is not reflexive, you can either give the counter example or you can prove it out. But here it's better if you give the counter example. Now, reflexivity. Now, as far as reflexivity is concerned, I am taking it on reals. So, obviously, A and B are reals only. Now, let A be equals to 1 by 2. So, 1 by 2 square is 1 by 4. And 1 by 2 is not even less than 1 by 4, not even equals to 1 by 4. So, R is not reflexive. Secondly, come as symmetricity. Now, in symmetricity, if A is less than or equals to B, say half is less than or equals to 1, then B is less than or equals to A gives 1 is less than or equals to half. Not possible again. So, R is not symmetric. Even now, as far as transitivity is concerned, you have in transitivity, you will write let A equals to say 5, B equals to say 3, and C equals to say 2. So you have A is less than B square, right? B is less than C square, but A is not less than C square, as 5 can't be less than or equals to 4. So R is not transitive. So this is the case where you have reflexivity, you have symmetricity, you have transitivity. And in this case, you have to give the example like this. Okay. Now, if I take up the case of, say, cube, define a relation R on reals as R equals to A comma B such that A is less than or equals to, say, B cube. Now, in the same way, you have to show whether R is reflexive, symmetric, or transitive. Now, reflexivity. Now, you can take same example. A is half. Half is less than or equals to 1 by 8. Not possible. So, not reflexive. Again, in symmetricity, you have half is less than or equals to 1, but 1 is not less than or equals to half cube. See, this you can also write as 1 cube. That's 1 only. So it's not even symmetric. Now, main example comes of transitivity. Now, in transitivity, you have to think of three numbers such that a is less than or equals to b cube, b is less than or equals to c cube, but a is not less than or equals to c cube. So take a as 10, b as 5, and c as 2. So 10 is less than or equals to 5 cube, 5 is less than or equals to 2 cube, but 10 is not less than or equals to 2 cube. So this is not even transitive. These two questions, a is less than or equals to b square, a is less than or equals to b cube, are very important. Now next question is give the example of the relation which is reflexive but not symmetric and not transitive. Give the example of the relation which is reflexive but not symmetric and not transitive. So I will take R1 as 1 1, 2 2, 3 3, 1 2, and 2 3. Now it's very clear it's reflexive, it's not even symmetric, it's not even symmetric here also, so it's not even transitive. So R1 is not symmetric, is reflexive, but not symmetric, as 1 2 is in R1, but 2 1 is not in R1. Even if you take 2 3 is in R1 and 3 2 not in R1, that will also work. And R1 is not transitive, as 1 2 is in R1, 2 3 is in R1, but 1 3 is not in R1. So I have given the example which is reflexive but not symmetric and not transitive. Now the second example is the relation which is symmetric but not reflexive, not transitive. So that's simple. R2 as say 1 2 and 2 1 on, of course, the set R as 1 2 3. So R2 is not reflexive, R2 is not transitive, R2 is just symmetric only. Now, what about transitivity? Now, I want to have the relation which is reflexive, which is not reflexive, not symmetric, but transitive. So R3 is 1 2, 2 3, and 1 3. Obviously, it's not reflexive, not symmetric, but it's surely transitive. So R1 is R3 is not reflexive, not symmetric, but transitive. Similarly, you can construct the relations. I give you exercise, the relations which are reflexive and symmetric but not transitive, transitive and symmetric but not reflexive, and symmetric and reflexive and transitive but not symmetric. Like this, three cases you can practice. I can write it out: reflexive and symmetric but not transitive. Second, symmetric and transitive but not reflexive. Third, reflexive and transitive but not symmetric. Now, last question. I defined the relation on all planes. Relation on all planes as R4 equals to set of all triangles, set of all relation in plane. Means many figures are there. Plane, a triangle is there, square is there, many other plane figures are there. So relation in the plane says set of all triangles in a plane such that T1 is congruent to T2. Obviously T1, T2 are the triangles in the plane and we have to show that it's congruence. Show that R4 is an equivalence relation. Now, for showing that R4 is an equivalence relation, R4 is reflexive. How? As congruent is triangle is congruent to itself. So T1 belongs to R4 and R4 is reflexive. R4 is symmetric as T1 is congruent to T2 implies T2 is congruent to T1. So R4 is symmetric. Now R4 is transitive as T1 is congruent to T2, T2 is congruent to T3 implies T1 is congruent to T3. So T1, T2 belongs to R, T2, T3 belongs to R implies T1, T3 belongs to R. And so you can write R is transitive and hence R4 is transitive and hence R4 is an equivalence relation. So today we have done 6 questions. Now I will leave it to you whether I should continue this further or should I start with next topic. Okay, I will take one more class. I will sort out all the things there and then I will take a test on this types of relations. Thank you class. Thank you very much.